3 January 1961, 9:01 p.m., Mountain Standard Time, Auxiliary Reactor. Area 1, National Reactor Testing Station, Idaho. A heat detection alarm trips at the security station, one of several that evening from the small Army reactor building. Outside, winter air holds at -15 Celsius. Inside, a maintenance shift proceeds under written instructions. Operators expect a subcritical core, control rods disconnected, water level lowered for instrumentation work. Remote radiation monitors near the building show background levels. Then, within 4 milliseconds, instrument traces record what procedures considered impossible. Reactor power surging to approximately 20,000 megawatts, more than 6,000 times rated capacity. A single control rod, withdrawn far beyond its intended reconnection distance, has driven the core prompt supercritical before any feedback can respond. The excursion ends itself almost as quickly as it begins. What remains? 3 fatalities, debris scattered across an operating floor, and dose fields that will define every decision for 2 years, will become the only immediate fatality reactor accident in United States history. 1954 through 1958, National Reactor Testing Station, Idaho Desert, approximately 40 miles west of Idaho Falls. An Army Nuclear Power Program briefing folder lies open on a conference table in Washington, describing a vision: compact nuclear reactors delivering electricity and heat to forward bases, radar stations, and Arctic outposts, where diesel fuel convoys struggle against weather and distance. The concept centers on simplicity: a reactor small enough to transport, reliable enough for minimally trained crews, powerful enough to replace generators burning fuel flown in at enormous cost. The Atomic Energy Commission and Army planners collaborate on several prototype designs. One becomes the Stationary Low-Power Reactor Number One, designated SL-1. Engineering documents describe a 3-megawatt thermal direct cycle boiling water reactor designed to produce roughly 200 kilowatts electric plus space heating. Argonne National Laboratory adapts an earlier low-power design. Combustion Engineering takes over as contractor operator. The AEC Idaho Operations Office oversees licensing and safety reviews. SL-1's site sits within the National Reactor Testing Station, an 890-square-mile federal reservation hosting dozens of experimental reactors. The facility occupies a section called Auxiliary Reactor Area 1, a cluster of low buildings in sagebrush and lava rock. To planners, this is one test bed among many. The reactor uses plate-type fuel assemblies enriched to approximately 93% uranium-235, arranged in a compact cylindrical core. 5 cruciform control rods, 1 central, 4 peripheral, manage reactivity. Water enters the bottom of the core, boils, drives a small turbine, and returns as condensate. No large containment dome, the building resembles an industrial test cell more than the massive structures rising at commercial sites. Documentation from the Department of Energy and Idaho National Laboratory summarizes the mission clearly. SL-1 is a small nuclear power plant designed to provide electric power and space heating for remote military facilities. The Army's requirement for field deployable power drives every design choice: compactness over redundancy, simplicity over elaborate safety systems, ease of operation over intensive training. These trade-offs appear reasonable for a prototype in a remote test range. Operational history begins in August 1958. The reactor achieves first criticality, runs through power ascension tests, and settles into a pattern of intermittent operation supporting Army training and AEC research. Crews rotate through. Procedures evolve from initial drafts into typed manuals. For 2 years, SL-1 operates as intended, modestly quietly with no significant incidents recorded in public summaries. Yet one design feature will later be cited as a departure from emerging safety philosophy. The central control rod, designated Rod 9, carries unusually high reactivity worth. Withdrawing it alone, without moving the other 4 rods, can add enough positive reactivity to make the core prompt critical. This single-point vulnerability reflects the compact geometry and the choice to load only 40 of 59 possible fuel positions, concentrating power toward the center. In the language of later standards, This configuration creates a one-rod criticality hazard, a condition that will become explicitly prohibited after SL-1's final night. On paper, SL-1 is a modest testbed for remote power. In the historical record, it will stand out not for megawatts delivered, but for a single rod's capacity to decide the reactor's fate. 1958 through 1960. SL-1 Reactor Building, Auxiliary Reactor Area 1, National Reactor Testing Station. A cutaway drawing on an engineering poster shows the reactor's internal arrangement, a small cylindrical pressure vessel, approximately 4 feet in diameter and 14 feet tall, sitting in a bed of gravel for biological shielding. Inside, the core holds 40 plate-type fuel assemblies in a square lattice designed for 59 positions. 5 cruciform control rods penetrate from above, one at the center, 4 symmetrically placed around it. Designers intended a straightforward, easily modeled geometry. Plate fuel, borrowed from research reactor practice, offers high surface area for heat transfer. Highly enriched uranium allows a compact core volume. The direct cycle arrangement eliminates heat exchangers and steam generators, reducing system complexity. For a prototype intended to validate field-deployable concepts, these choices align with program goals. In practice, leaving 19 lattice positions empty increases local power peaking in the loaded central region. Neutron calculations show that the central control rod, Rod 9, must absorb a disproportionate fraction of excess reactivity to keep the core subcritical during shutdown. Operating procedures note that Rod 9 alone carries enough negative reactivity that its complete withdrawal, moving it from fully inserted to fully out, adds approximately $4 of positive reactivity, well above the prompt critical threshold of $1. Technical reviews from Argonne and Combustion Engineering acknowledge this rod worth but conclude it acceptable for a low-power test reactor, operating under controlled conditions with trained personnel. The assumption is that control rods move only under drive mechanism control, with interlocks and procedural limits preventing inadvertent large withdrawals. Manual handling of rods, required during certain maintenance tasks, is governed by written instructions specifying limited movement. Post-accident analyses by Los Alamos National Laboratory and NASA document the core's reactivity characteristics in detail. One summary states that rapid withdrawal of the central control rod to about 20 inches resulted in an accelerated nuclear reaction condition known as a prompt criticality. This sensitivity, where a single rod's position determines whether the core remains safely subcritical or goes prompt critical, reflects the concentration of fissile material and the absence of geometric or physical barriers to rapid reactivity insertion. The decision to use this configuration in SL-1 is not reckless by the standards of the late 1950s. Test reactors in Idaho and elsewhere operate with experimental cores, often pushing boundaries to gather data. SL-1's design passes AEC safety reviews. Training materials emphasize the importance of following rod movement procedures. Operators are briefed on rod worth and the need for deliberate, controlled actions during maintenance. Yet the compact geometry that makes SL-1 appealing for remote deployment also creates a latent vulnerability, a design where a single misexecuted manual step during maintenance can, by itself, drive the reactor prompt critical. In later reactor design standards, this will be recognized as unacceptable. The principle will be codified. No reactor core shall be capable of reaching prompt criticality through the movement of any single control element, regardless of operator action or mechanical failure. Before January 1961, this configuration is accepted. After, it becomes a cautionary boundary. February 1959 through 23 December 1960. SL-1 Facility, Auxiliary Reactor Area 1. A floor plan drawing shows the reactor building's vertical arrangement, the pressure vessel and gravel shield at the bottom level, the operating floor above with control rod drives and turbine equipment, and a fan room on top connecting to exterior. Ventilation ducts. Access comes through a support building designated ARA 603, then up enclosed stairways to the operating floor. The structure lacks the massive concrete containment shells being built for commercial reactors. SL-1's building is a thin-walled industrial enclosure in desert isolation. This compact layout serves the Army's vision of a transportable, field-deployable power plant. It also means that the operating floor sits directly above the reactor vessel with minimal shielding between levels. During normal operation, this presents no issue. Coolant water and structural materials provide adequate radiation protection. During an accident with core damage or high radiation fields, responders must work in a constrained vertical space where dose rates can vary dramatically over short distances. Maintenance procedures for SL-1 include periodic testing of control rod drop mechanisms. When a scram signal is initiated, each rod should fall freely into the core under gravity, inserting negative reactivity within seconds. Operational logs document drop test results. Between February 1959 and 18 November 1960, approximately 40 instances occur where a control rod sticks during or after a scram test, a failure rate near 2.5%. These events are noted, rods are manually freed, and testing continues. Between 18 November and 23 December 1960, the pattern changes. In just over 5 weeks, 23 additional stuck rod events are recorded, a failure rate jumping to approximately 13%. The increase suggests mechanical degradation, wear in the drive mechanisms, misalignment between rod and guide structures, or accumulation of corrosion products that impede smooth motion. Congressional testimony after the accident reveals that the project manager, W.B. Allred, was not completely aware of this sharp rise in failure frequency. He later states that had he known, he would have ordered a plant shutdown for detailed examination and possible redesign of the rod drive system. Yet no such shutdown occurs. Maintenance continues under existing procedures. One procedure, required when control rods are disconnected from their overhead drives for instrumentation work, calls for manual reconnection. An operator must lift each rod by hand approximately 3 to 4 inches, just enough to engage a ball on the rod's upper end with a latch on the drive mechanism. This step assumes rods move smoothly and predictably under manual force. 3 men are scheduled for the evening shift on 3 January 1961. Army Specialist John A. Burns, trained as a reactor operator, Army Specialist Richard Leroy McKinley, also an operator, and Navy Construction Electrician First Class Richard C. Legg, the shift supervisor. Their names appear in Atomic Energy Commission reports, Department of Energy accident summaries, and later historical accounts. All 3 are experienced with SL-1 systems and familiar with maintenance procedures. One detail from operational records stands out in retrospect. While control rods frequently stuck during automatic drop tests, no log entry documents a rod sticking during the manual reconnection procedure. This absence of prior incidents may have reinforced confidence that manual handling, performed slowly and carefully, posed minimal risk. On the evening of 3 January, that assumption will be tested under conditions no procedure anticipated. 23 December 1960 through 3 January 1961 afternoon. SL-1 facility, Auxiliary Reactor Area 1, National Reactor Testing Station. A control room log entry, dated and initialed, records SL-1 placed in cold shutdown on 23 December. 11 days of maintenance stretch ahead. Instrumentation calibration, installation of cobalt flux wires to refine power distribution measurements, and routine mechanical work. Restart is scheduled for early January. To the Atomic Energy Commission Idaho Operations Office and Combustion Engineering staff, this is standard outage procedure. Nothing flagged as off-normal. No special hazards beyond routine radiological controls. The scope of work includes lowering reactor water level to permit access for installing approximately 44 cobalt flux wires in the core. These wires, when activated by neutron flux during subsequent operation, will provide detailed data on power distribution across fuel assemblies. Control rods must be disconnected from their overhead drives to avoid interference during wire installation. Procedures specify that with rods decoupled and water level reduced, the core remains subcritical by a comfortable margin. Multiple rods would need to be withdrawn simultaneously to approach criticality. Written restart instructions approved by AEC oversight outline the sequence: complete flux wire installation, verify mechanical clearances, manually reconnect control rods to their drives, restore normal water level, and conduct a controlled approach to criticality under instrument monitoring. Each step appears bounded by procedures developed over 2 years of SL-1 operation. Combustion Engineering's project manager and plant operations supervisor rely on these written procedures. Later congressional hearings will reveal gaps in communication. The sharp increase in control rod sticking incidents during November and December was not fully conveyed up the management chain. Field-level operators and maintenance staff knew rods were sticking more frequently, but formal escalation to senior decision-makers did not occur. The interim AEC report, designated IDO 19300, will document this oversight lapse as a contributing factor. By the afternoon of 3 January 1961, the outage framework is in place. Flux wires have been installed, mechanical systems have been inspected. The remaining tasks, reconnecting, control rods and refilling the vessel, are scheduled for the evening shift. 3 men will perform the work, the shift supervisor and 2 operators, alone in the reactor building with no continuous on-site oversight beyond periodic checks from support staff. In hindsight, this configuration concentrates multiple risk factors into a single shift: decoupled rods, lowered coolant, reduced staffing, limited supervisory presence, and a manual operation on the highest worth control element in the core. Each factor, individually, fits within accepted practice. Combined, they create a condition where a single procedural deviation can have system-level consequences. The written plan describes an 11-day outage and routine restart. In practice, every critical step between shutdown and planned startup will compress into the final hours of the final evening, inside a building where 3 coffee cups and 3 jackets wait in the support area, personal effects that will later help investigators reconstruct who was present and where. 3 January 1961, 4 p.m. through 9 p.m. SL-1 facility, National Reactor Testing Station. Control room logs document shift change at 1600 hours. 3 men arrive to complete the evening's work: John Burns, Richard McKinley, and Richard Legg. In the support building, 3 jackets hang by the door. 3 coffee cups sit on a table, still holding liquid when investigators arrive hours later. Small domestic details that mark the boundary between routine and catastrophe. Day shift crews have finished mechanical tasks: flux wire installation, shielding block repositioning, and verification of instrumentation. Outdoor temperature drops toward -15 Celsius, typical for an Idaho winter night. The reactor building, unheated during shutdown, holds the cold. The evening shift's assignment is straightforward: reconnect the 5 control rods to their overhead drive mechanisms, restore normal water level, and leave the plant in a condition ready for controlled startup on 4 January. The reconnection procedure requires manual handling. With drives disconnected, each control rod rests on its lower grid support, held only by gravity. To re-engage the drive, an operator must grasp the rod's upper structure and lift it approximately 4 inches, 10 centimeters, enough to align a ball at the rod's top with a latch on the drive mechanism. Once the latch engages, the drive motor can be tested for proper connection. The procedure assumes smooth, predictable rod movement and specifies that lifting should be gradual and controlled. Post-accident reconstructions, drawing on the AEC Board of Investigation report and later analyses, outline likely task assignments. Burns, as the operator most familiar with the rod reconnection process, would perform the physical lifting. Legg, as shift supervisor, would position himself on or near the reactor vessel, head to observe and verify proper engagement. McKinley would assist nearby, monitoring instruments or preparing for the next procedural step. These inferences come from the positions in which the men are later found, and from operational practice at SL-1. At this point in the evening, no alarm has sounded. Instruments show expected readings for a cold, subcritical reactor. Radiation levels in the building are at background. The written procedure sits on a clipboard or taped to a wall, standard practice for guiding maintenance work. Nothing in the available records suggests the crew anticipated difficulty, yet one factor distinguishes this evening from earlier maintenance periods: the degraded condition of control rod drive mechanisms, reflected in the 23 stuck rod events recorded between mid-November and late December. While operators knew rods sometimes required extra force to free during drop tests, no documented instance exists of a rod sticking during manual reconnection. This absence of prior problems may have shaped expectations that the task posed minimal risk. The procedure specifies lifting rod 9, the central highest worth rod, approximately 4 inches. Later, physical evidence will indicate movement of approximately 20 inches, 50 centimeters, 5 times the intended distance. This discrepancy between procedural intent and actual movement becomes the central technical fact of the accident. At 9:01 p.m. Mountain Standard Time, the gap between procedure and execution closes in 4 milliseconds. The 3 men on the operating floor have no time to react. The reactor's response, a prompt critical power excursion, is governed entirely by physics, not by human decision or intervention. Outside, the last expectation on 3 January is that SL-1 will be ready for startup the next morning. Inside, that expectation ends the instant Rod 9 begins moving beyond its reconnection range. 3 January 1961, 9:01 p.m., SL-1 reactor vessel and operating floor, Auxiliary Reactor Area 1, a single control rod movement, recorded only through its physical consequences and instrument traces, initiates a sequence that unfolds faster than human perception. At 9:01 p.m., Mountain Standard Time, Rod 9 is withdrawn from its seated position. The movement extends far beyond the intended 4-inch reconnection lift. Post-accident analysis, combining physical evidence with neutronics calculations, estimates withdrawal of approximately 20 inches, half a meter. This movement adds positive reactivity rapidly. The SL-1 core, with its compact geometry and highly enriched fuel, responds within milliseconds. Neutron population doubles, then doubles again, each generation taking microseconds. The reactor crosses delayed critical, where neutron production depends on delayed neutrons from fission product decay, and enters prompt critical, where prompt neutrons alone sustain and accelerate the chain reaction. Reactivity insertion exceeds $1, the threshold where control becomes instantaneous and total, governed solely by physics. NASA's supercritical accident case study, drawing on AEC technical analyses, estimates that reactor power reaches approximately 20,000 megawatts in roughly 4 milliseconds, more than 6,000 times the 3 megawatt thermal rating. Energy released in this brief pulse totals approximately 133 megajoules, equivalent to about 4.4 times 10 to the 18th fissions. This energy deposits directly into fuel plates, coolant water, and nearby structures. Fuel plates, designed for steady low-power operation, experience extreme thermal stress. Some plates melt, others warp or fracture. Coolant water adjacent to the hottest fuel flashes instantly to steam. The rapid phase change creates a pressure wave, a water hammer, that propagates through the vessel at high velocity. Pressure peaks near 10,000 pounds per square inch in localized regions, with an average pressure around 500 psi across the vessel head. The reactor vessel, weighing approximately 26,000 pounds, absorbs this upward impulse. It lifts roughly 9 feet, 2.7 meters, striking the overhead crane and support structures before settling back. Shield plugs atop the vessel eject upward, some penetrating the ceiling above. Gravel from the biological shield bed scatters across the operating floor. Control rods, fuel debris, and activated materials disperse into the building atmosphere and onto surfaces. The 3 men on the operating floor are struck by ejected components, high-velocity water, and structural impacts. Autopsy records and the AEC Board of Investigation findings make clear that death results from mechanical trauma, blunt force, penetrating injuries from shield plugs and debris, not from acute radiation exposure during the 4 millisecond pulse. Richard Legg is found pinned to the ceiling by a shield plug. John Burns and Richard McKinley lie on the operating floor, both with severe injuries consistent with impact and pressure effects. The Atomic Energy Commission interim report, designated IDO 19300, summarizes the initiating event in technical language. The reactor was shut down for maintenance, and at 9:01 p.m. Rod 9 was withdrawn too far, a precise engineering description of the single action that triggered the excursion. This phrasing, restrained and factual, appears repeatedly in formal accident analyses. By 9:01 and 1/2 p.m., core power has already dropped back near zero. The water hammer and core disassembly provide strong negative reactivity feedback, terminating the chain reaction as abruptly as it began. No sustained power generation follows. The reactor is physically incapable of sustaining criticality after the excursion disrupts core geometry. Yet the consequences, mechanical destruction, 3 fatalities, and radiation fields from activated materials and fission products, will persist. The chain reaction shuts itself down almost as quickly as it starts. The mechanical imprint and radiological signature of those 4 milliseconds, scratches on a rod, a displaced vessel, debris patterns, and 3 bodies, become the central evidence for every investigation that follows. 3 January 1961, 9:01 through 9:30 p.m., National Reactor Testing Station Fire Station and SL-1 Support Building. A heat detection alarm sounds at the NRTS Central Fire Station at 9:01 p.m., automatically transmitted from sensors in the SL-1 building. The log entry notes this as the 3rd alarm from Auxiliary Reactor Area 1 that day. Earlier alarms traced to equipment malfunctions or environmental conditions produced no emergency. Duty personnel initially suspect another false signal. Standard response protocol dispatches a fire crew regardless of alarm history. Firefighters board a truck equipped with self-contained breathing apparatus, portable radiation survey meters, and standard firefighting equipment. The drive to AR-1 covers several miles through the dark desert reservation. Outside, temperature holds near -15 Celsius. Roads are clear but cold. Approaching the SL-1 facility, crew members see no obvious signs of fire, no smoke, no visible flame, no thermal glow from windows. The building exterior appears normal. A survey meter reading taken near the perimeter fence, however, shows elevated radiation levels, approximately 25 Roentgen per hour, compared to typical background of a few tens of micro-Roentgen per hour. This reading, a 1,000-fold increase, indicates something far outside normal conditions. Firefighters proceed cautiously donning air packs. They enter the support building, ARA 603, expecting to find the 3-man crew. The room appears lived in. Jackets hang by the door, coffee cups sit on a table, personal items rest on shelves. No personnel are present. This absence, combined with high external radiation readings, shifts the response from routine alarm to potential reactor incident. A health physicist arrives within minutes, bringing additional survey equipment and dosimetry. Readings inside the support building remain near background, but measurements taken near the stairwell leading up to the reactor operating floor show increasing dose rates. The crew debates entry. Radiation levels are high, the crew's location is unknown, and the nature of the incident remains unclear. The decision is made to proceed with a rapid reconnaissance. 2 firefighters, equipped with air packs and self-reading dosimeters, ascend the stairs toward the operating floor. Opening the door at the top, they encounter a chaotic scene. Gravel and debris scattered across the floor, damaged equipment, and, critically, 2 bodies visible in abnormal positions. Survey meters spike, registering dose rates far above the initial perimeter readings. In some areas near the reactor vessel and overhead structures, fields approach 500 Roentgen per hour. One man, Richard McKinley, shows slight movement, indicating he may still be alive. The rescue decision is immediate. Extract the survivor. 2 firefighters enter, working quickly to reach McKinley, lift him, and carry him back down the stairs. Dose rates limit the time available. Each second of exposure adds measurable dose to the rescuers. The operation succeeds in under 2 minutes. McKinley is placed in an ambulance and transported toward medical facilities. Later surveys of the ambulance reveal significant radioactive contamination, requiring the vehicle to be taken out of service for decontamination. This contamination comes from activated materials and fission products transferred from McKinley's body and clothing, a preview of the radiological complexity that will define the entire recovery operation. By 9:30 p.m., responders recognize that standard firefighting protocols are inadequate. 2 bodies remain inside the building. Dose fields are high and variable. The reactor core is in an unknown condition. What began as a routine alarm response has become a radiological recovery operation requiring specialized planning, equipment, and personnel. 3 January 1961, 9:30 through 11 p.m. SL-1 operating floor and ambulance staging area, National Reactor Testing Station. a small group of firefighters and health physicists, now understanding the radiological hazards, prepare for controlled entries into the reactor building. Self-reading dosimeters are distributed and calibrated. Each entry will be timed and limited by preset dose budgets calculated to keep individual exposures below emergency thresholds. The immediate objective is to extract John Burns, whose body is visible on the operating floor, and to locate Richard Legg, who is reported to be the third crew member but has not yet been seen by responders. Survey data from the initial reconnaissance shows dose rates on the operating floor ranging from tens of Roentgen per hour in access pathways to several hundred Roentgen per hour near the reactor vessel and overhead crane. To place these numbers in context, natural background radiation averages approximately 2 to 3 millisieverts per year, roughly 0.2 to 0.3 Roentgen per year. Evacuation guidance for nuclear incidents typically considers projected doses of 10 to 50 millisieverts. The fields inside SL-1's reactor room represent exposure rates hundreds to thousands of times higher than background, with potential for significant acute dose in minutes. Firefighters equipped with Scott air packs and protective clothing make repeated brief entries. The first priority is moving Burns's body to a lower dose area, where it can be prepared for transport. Each entry lasts less than 2 minutes. Responders work quickly, guided by flashlights and the scattered emergency lighting. Still functioning in the building, some air packs malfunction in the sub-zero air, seals failing as cold contracts materials. At least one firefighter briefly removes his mask to complete a task, accepting elevated exposure to achieve the mission. During these operations, responders discover Richard Legg's location. He is pinned to the ceiling structure above the reactor vessel by a shield plug that ejected upward during the excursion. This position places him in the highest dose region of the building, fields near 200 Roentgen per hour at contact with activated metal surfaces. Immediate extraction is judged impossible without specialized equipment and shielding. The decision is made to focus on removing Burns and securing the building, deferring Legg's recovery to a later phase with better preparation. Burns's body is successfully moved to the ambulance staging area by approximately 11 p.m. Contamination surveys show significant activity on clothing and exposed skin, requiring careful handling and documentation. Transport to pathology facilities will require coordination with radiological safety staff to manage contamination control during autopsy. The Department of Energy's SL-1 Recovery Operation Report later documents that approximately 22 individuals receive whole-body radiation exposures between 3 and 27 Roentgen, 30 to 270 millisieverts, over the entire course of recovery operations. Many of the highest single-shift doses occur during this initial night, when urgency, incomplete information, and the hope of finding survivors drive aggressive entry decisions. As responders regroup outside the building after midnight, the operational picture clarifies. One victim has been transported to medical care, but will die en route. One body has been removed. One body remains inside in a high-dose location requiring engineered solutions. The reactor core is physically disrupted, incapable of resuming power operation, but still presenting intense radiation fields from fission products, activation products, and fuel debris. What began as a potential rescue mission has become a recovery operation and a radiological engineering challenge. The SL-1 building, designed as a modest test facility, now contains conditions that will require months of planning, specialized equipment, and carefully managed exposures to resolve. 4 through 9 January 1961. SL-1 building, Auxiliary Reactor Area 1, National Reactor Testing Station. A recovery planning sketch posted in a temporary command center maps radiation fields by location, up to 200 Roentgen per hour near the reactor vessel, and at the ceiling where Richard Legg's body remains pinned, elevated readings through access routes, and lower but still significant fields in the fan room and stairwells. These measurements, compiled from multiple survey entries, define the radiological environment recovery teams must navigate. Standard emergency response plans, developed for reactor incidents, envision brief entries after a reactor trip or controlled shutdown. SL-1 presents a different scenario: core physically disrupted, high-dose fields persisting from activated structures, and dispersed fission products, and objectives that require sustained work in close proximity to radiation sources. Recovering Leg's body becomes the focus of engineering effort. Teams from General Electric, the Atomic Energy Commission, and Army units rotate through tasks under close monitoring by health physics staff. Each entry is time-limited, with exposure budgets calculated to keep individual doses within emergency limits. For the hottest zones, entry times are capped at approximately 65 seconds, barely enough to position equipment, perform a single task, and retreat. Specialized equipment is brought to the site. A Manitowoc Model 3900 crane is modified with a 5.25-inch steel shield and a 9-inch lead glass viewing window, allowing an operator to work near high radiation areas with reduced dose. Remote-operated tools, long poles with hooks, cutting torches on extended arms, are fabricated in AEC shops and transported to AR-1. A shielded workbox, essentially a lead coffin with armholes, permits a welder to perform structural cuts at elevation, while remaining partially protected. The task requires coordinated steps, removing overhead obstructions, cutting structural elements that block access, positioning lifting equipment, and finally extracting the body in a controlled manner. Each step is rehearsed outside the building using mock-ups. Entry teams practice movements to minimize time in high-dose areas. Health physicists monitor dosimeters in real time, calling teams out when preset limits are approached. On 9 January 1961, after multiple entries over 5 days, Leg's body is successfully removed from the ceiling structure. The operation involves carefully maneuvering around activated metal, using remote tools to free the shield plug pinning the body, and lowering the remains to the operating floor before final transport out of the building. Total accumulated dose for the team performing this final phase exceeds that of any prior single task in the recovery. The Department of Energy's final recovery report records that approximately 790 people incur measurable radiation dose during the months-long SL-1 recovery and cleanup. The 22 highest exposed individuals receive whole-body doses between 3 and 27 Röntgen, 30 to 270 millisieverts. For comparison, typical annual occupational dose limits in the 1960s are 5 Röntgen per year. These recovery workers receive multi-year equivalent doses in weeks. Once the last body is removed, operational focus shifts from human recovery to equipment stabilization and site characterization. The same radiation that complicated rescue now becomes a tool. Dose rate measurements and contamination surveys map the distribution of fission products and activated materials, providing data that will support accident reconstruction and core physics validation. High-dose fields convert what might have been a simple retrieval into a technically complex months-long project that establishes templates for radiological recovery planning used in later nuclear incidents worldwide. January through mid-1961, pathology and laboratory facilities designated for handling SL-1 victims and samples. A small brass watch case removed from John Burns's body is placed under a gamma-ray spectrometer. The analysis detects copper-64, a short-lived isotope produced when stable copper-63 captures a neutron. Similar activation products appear in other metal objects: a cigarette lighter screw, a key ring, a belt buckle. These items, treated not as personal effects but as neutron dosimeters, provide direct physical evidence of the intense neutron flux during the 4-millisecond excursion. Conventional autopsy procedures assume minimal radiological hazard from remains. SL-1 forces a departure from standard practice. Parts of the victims' bodies and clothing emit dose rates up to approximately 1,500 Röntgen per hour at contact, high enough to require lead shielding, remote handling tools, and strict time limits for pathologists and technicians. The bodies themselves are contaminated with fission products and activated materials from the reactor environment. Forensic teams work under these constraints to determine cause of death and reconstruct victim positions at the time of the accident. Los Alamos National Laboratory and other AEC facilities provide technical support. The goal is not only medical, establishing that mechanical trauma, not acute radiation, caused death, but also neutronic, using activation of materials on and in the bodies to validate reactor physics models of the power excursion. Gamma spectroscopy of metallic objects reveals isotopes with known production cross-sections and half-lives. Copper-64, with a 12.7-hour half-life, provides time-sensitive data on neutron exposure just hours before the accident. Gold-198 produced in gold jewelry and watch components, offers another marker. Analysis of hair samples detects phosphorus-32, created when stable phosphorus-31 absorbs a neutron, a direct biological indicator of neutron dose to tissue. By comparing activation levels in objects worn on different parts of the body, investigators infer distance and shielding from the core at the moment of criticality. These data, combined with the positions where bodies were found, support the reconstruction that Richard Legg stood on, or very near the reactor vessel head. John Burns stood nearby at the operating floor level, and Richard McKinley was positioned slightly farther, away. The gradient of neutron activation matches the expected inverse square fall-off from a central source, validating that the core itself was the neutron emission point. Autopsy documentation, summarized in Los Alamos reports and AEC accident reviews, clearly states that death resulted from mechanical injuries, blunt trauma from ejected components, penetration by shield plugs, and impacts from the vessel's upward motion. Radiation exposure during the excursion, while significant, was not the proximate cause of death. This finding differentiates SL-1 from scenarios where acute radiation syndrome is the primary mechanism. Burial arrangements reflect the radiological reality. Richard McKinley's remains, buried at Arlington National Cemetery, require a double lead-lined casket and a reinforced concrete vault, measures documented in cemetery records. Similar precautions apply to John Burns and Richard Legg. These are not ceremonial choices, but engineering requirements to contain long-lived activation products and prevent environmental release. The forensic work yields a dual legacy: medical clarity on cause of death and a unique data set linking biological activation to reactor neutronics. The activated objects serve as inadvertent dosimeters, creating a physical record of the neutron field that validates computational models and provides quantitative confirmation of prompt criticality, evidence that could not be obtained from instrument traces alone. 1961 through 1962. Atomic Energy Commission Board of Investigation, Washington, D.C., and Examination Facilities, Idaho. A segment of Control Rod 9 lies on an examination table inside a hot cell, surface scratches visible under magnification. Technicians measure the marks carefully, comparing them to alignment features inside the reactor vessel. The scratches terminate at a position approximately 20 inches above the rod's normal fully inserted location, 5 times the intended withdrawal distance for reconnection. This physical evidence, combined with neutronics calculations, anchors the central finding of the AEC investigation. Rod 9 was withdrawn about 20 inches, and this movement alone was sufficient to drive the core prompt critical. No combination of other factors, water level, temperature, or position of the other 4 control rods, can account for the magnitude of the reactivity insertion without this single large rod movement. To test the plausibility of such a withdrawal, investigators construct a mock-up using a control rod of identical weight and geometry. Experiments show that a single operator, applying moderate upward force, can lift the rod to the 20-inch position. If the rod is stuck, jammed by misalignment or friction, and then suddenly releases, the operator's sustained lifting force can result in rapid overtravel. These tests demonstrate mechanical feasibility, but cannot determine whether the movement on 3 January was deliberate, accidental, or the result of a stuck-then-released scenario. Congressional hearings convened after the accident bring forward testimony from SL-1 management. Project manager W.B. Allred states that he was not completely aware of the sharp increase in control rod sticking incidents between mid-November and late December 1960. He acknowledges that had the frequency of stuck rod events been escalated to him, he would have ordered a plant shutdown for detailed examination and possible redesign of drive mechanisms. This testimony highlights an organizational gap. Field-level awareness of hardware degradation did not translate into management action. The AEC board's final report synthesizes physical evidence, neutronics analysis, and operational history into a causal chain, a compact core design giving one rod high reactivity worth, degrading mechanical systems, increasing the likelihood of unpredictable rod behavior, limited procedural safeguards against over-withdrawal during manual handling, and insufficient supervisory oversight during maintenance. Each link is documented. The chain as a whole explains how the accident became possible. Yet one question remains unanswered by the available evidence. Why did the operator, most likely John Burns based on his assigned role, withdraw rod 9 approximately 20 inches when procedures specified 4 inches. 3 explanatory scenarios appear in subsequent analyses: deliberate action for reasons unknown, accidental over-travel after freeing a stuck rod, or some combination of factors not captured in the record. The board's report notes that the reason for the rod withdrawal will never be known with certainty because all 3 crew members died in the accident and no instrumentation recorded operator actions in real time. This gap between quantitative precision, we know exactly how far the rod moved and what physics that movement caused, and qualitative uncertainty, we do not definitively know why the movement occurred, shapes SL-1's place in safety culture. The accident becomes a case study not only in reactor physics and design vulnerabilities, but also in the limits of reconstruction when key witnesses are lost. The investigation quantifies rod travel, energy release, mechanical damage, and dose fields with scientific rigor. It identifies design and organizational weaknesses that permitted a single manual action to have catastrophic consequences. It recommends changes to design standards, procedures, and oversight, but it cannot, from the physical evidence alone, reconstruct the moment-by-moment decisions of 3 men working in a cold reactor building on a winter night, leaving one aspect of SL-1's history permanently incomplete: 1961 through 2000. SL-1 site and burial ground, Idaho National Engineering Laboratory. Aerial photographs from 1962 show the SL-1 building dismantled and a new earthen mound approximately 1,600 feet to the northeast, fenced and marked. The burial ground contains contaminated structural materials, reactor components, soil and debris from the accident and subsequent recovery, approximately 99,000 cubic feet of radioactive waste. Initial plans considered shipping high-activity items off-site to specialized disposal facilities. Risk assessments, however, show that transporting contaminated materials through populated areas and handling them at multiple locations would expose workers and the public to greater cumulative dose than on-site burial. The decision is made to excavate disposal cells near the accident site, place materials in lined pits, and cap with clean soil. General Electric, under AEC contract, leads the cleanup. The reactor vessel itself is moved to a hot shop for detailed examination before final disposition. Smaller components, piping, electrical systems, and building materials are surveyed, packaged, and buried. Contaminated gravel from the biological shield and soil from around the building join the inventory. By 1963, the original SL-1 structure is gone. The burial ground becomes the site's most visible feature. Environmental monitoring begins immediately and continues for decades. Aerial gamma surveys flown in 1974, 1982, 1990 and 1993 use sensitive detectors to map surface and near-surface radiation fields across the Idaho National Laboratory site. These surveys consistently identify the SL-1 burial ground as an area with elevated readings, primarily from cesium-137, a fission product with a 30-year half-life. Ground surveys in 1994 record dose rates of approximately 0.5 milliroentgen per hour at 0.75 meters above the burial surface, compared to local background of about 0.2 milliroentgen per hour. The site becomes part of the Idaho National Laboratory's Comprehensive Environmental Response, Compensation and Liability Act program, Superfund oversight. Records of decision in 1996 and 2000 specify long-term remedies: containment by capping with an engineered barrier constructed primarily of native materials, institutional controls to prevent intrusion, and periodic inspection to verify cap integrity. The engineered cap, completed in 2000, uses multiple layers of soil, gravel, and clay to minimize water infiltration and maintain surface stability. Monitoring continues into the 21st century, with periodic surveys confirming that contamination remains contained within the burial footprint. Dose rates decline slowly as cesium-137 decays, but the site will require oversight for many human generations. One brief excursion commits federal agencies to decades of monitoring, periodic surveys, and institutional controls, quantifying how a 4-millisecond event creates a long-term land management obligation. 1962 through present, Reactor Design Standards and Military Power Programs, United States and internationally. A modern safety analysis slide displayed in a university nuclear engineering classroom lists a fundamental requirement. The reactor core must remain subcritical even if the most reactive control rod is stuck fully withdrawn. This principle, the one stuck rod criterion, appears in regulatory guidance, industry standards, and design reviews as a baseline safety requirement. Its origin traces directly to SL-1. Before January 1961, compact test reactors with high-worth control elements were considered acceptable under controlled conditions with trained operators. SL-1's design passed Atomic Energy Commission safety reviews. After the accident, that configuration becomes an example of what regulatory bodies will no longer permit. The lesson is codified. No reactor core shall be capable of reaching prompt criticality through withdrawal of any single control element, regardless of operator action or mechanical failure. Post-SL-1, design standards expand beyond the stuck rod criterion. Emergency instrumentation ranges are increased to cover high-power transients that earlier designs assumed impossible. Procedures lengthen from brief checklists to comprehensive manuals with multiple verification steps. Human factors analysis becomes a formal element of safety reviews, examining how maintenance tasks can be misexecuted under realistic conditions. The Army Nuclear Power Program, which commissioned SL-1, continues briefly with other reactor projects. The Mobile Low-Power Reactor, ML-1, operates at full power only a few months before corrosion issues, and cost overruns force shutdown. By the mid-1960s, the Army withdraws from reactor operations, concluding that conventional power sources and grid connections better serve military needs. The vision of field-deployable nuclear power, so attractive in the 1950s, fades as logistical and safety complexity outweigh perceived benefits. Los Alamos National Laboratory, NASA, and educational institutions worldwide adopt SL-1 as a case study in criticality safety, emergency response, and forensic reconstruction. The accident's quantitative record, rod travel measurements, power excursion calculations, dose field mapping, and recovery operation documentation provides data that remain relevant for training engineers and health physics professionals decades later. Standard nuclear safety references summarize the legacy in consistent language. The SL-1 accident caused SL-1's design to be abandoned and future reactors to be designed so that a single control rod removal could not produce very large excess reactivity. This phrasing appears in textbooks, regulatory documents, and historical reviews, anchoring a technical lesson to a specific historical event. More than 60 years after 3 January 1961, SL-1 remains the only United States reactor accident with immediate operator fatalities. Its burial ground, visible in aerial surveys, and its technical legacy, embedded in design standards, form a dual memorial. One physical, contained within an engineered cap in the Idaho desert, and one procedural, woven into every control rod design and safety analysis performed since. The final documented line is clear. A 4-millisecond excursion in a small test reactor changed how the world builds and operates nuclear power systems.